I come here, so I have my final solution P3HT PVDF-HFP with 2 channel, as you can see, the after galvanic exchange. So I'm just keeping it in the hot plate. The hot plate is not that much hot, it's just a little bit warm. And what I will do is, like, I will program the spin coater to spin coat semiconductor over that. So let's see how we can do that. So let's select recipe number 8 and go to step, select step 1 and it's called speed, select 2500 RPM, go to RAM and get selected 500 RPM. So So let's check if everything is okay. Turn on the key. Select this 8. Go. Yeah, this is 205. So it's okay, it's looking great. So we are almost done with everything. We have the semiconductor prepared. Also we have the 2-channel based electrode. All we need to do is we need to spin coat it. So let's go on and spin coat the semiconductor. So what I'll do is, first of all I need to check it out a little bit. But as I said earlier, you always need to check our instrument is this instrument, so I have just turned on the instrument. So and let's see, yeah, the RPM is moving fast and it's 2500 RPM. Quite okay, I think. So let's get started with it. But for some reason I am thinking of doing it at 2000 RPM because maybe that would be better, because we have to semiconductors. Or what you can do is you can put on it because then and then there is 1000. So let's look at the recipe. I want to do the step 1. I want to change this to 500. That is all. And this let's turn off the video. So one of the things you need to make sure is that when you are using this semiconductor, actually organic semiconductor, you need to be very careful here because the semiconductor is very sensitive to everything. So only take the least amount of time to take semiconductor and put it on the electrode for the spin coat. So close the lid as soon as possible. So I will open up the top of that. What I need to do is since we have 2 channels, I will order service to make each channel individually. So if you have 8 channels, so 8 times, 1 time. So that will make sure that spin coat is proper. You don't need to take a lot of time. third one. So you need to make sure that it is very fast so that this spin coating is uniform and it's thin so that the device will be more beautiful. So as I have two semiconductor channel, I will be using one after another. So let's start with the first one. I will start with the big one. So what I'll do is I'll just take a little and then drop it on the semiconductor. Since I am using from my left hand for the diamonds, just pull it in and just down. That's it. And also stop the lid and take as small time or just leave it as you want. Also, what I am doing is I am opening up a hot plate and making it at 60-degree temperature because after heating I will be needing to bake it a little bit. Yeah, the process heating is done. Now it's time for the second one. Similarly, just follow the same procedure. All you need to do is take a little bit of the temperature and that's it. Very good. Now close it. Glaze properly and after this filtering is done, all you need to do is you need to take it a little bit. I've already started the hot plate at 60 degrees. Turn on the big one, type in place. As you can see, this is the spin coating. If I just take it over to this, so you can see this is properly spin coated. Right. So spin coating is done now. All I need to do is I just need to keep it in the hot plate and make it just heat it a little bit. Let's take around 2 minutes for this thing. So I'll just start the timer here. So I'll take only 2 minutes. So time is up. We don't need to wait anymore. You can just stop it and take this for the measurement. So organic semiconductor preparation is done. Now we just need to use the dielectric ion gel and measure it. So let's go to the measurement process. We are going to measure the semiconductor. So first of all, what we need to do here, let me just give you a quick overview. These parts here is our conductor. The middle here vertical line here is our channel, and over the channel the little bit of darker gray area here. These are the galvanized, not galvanized, sorry, ion exchanged parts for like increasing conductivity and something like that. About that here, this light, but I don't know what's the color. It may be pink. So this is the semiconductor. Now we are going to, as you can see, this is bottom contact and top gate semiconductor. So we will be using our gate probe on top. This to be source and drain, and also as you know, on the gate terminal we need to put some dielectric. So we will be using organic ion gel based dielectric. So this is an ion gel, uh, dried out ion gel. So this is a dried ion gel. I have already cut it in small pieces. So what I'll do is I'll take some of these pieces from here and will try to put this on our channel so that we can put the gate contact over these ion gel particles and can visit the device. So here we go. Make sure your ion gel doesn't only is over the semiconductor, not over the contact. So you need to be very careful here. Let's go to the next one. Okay, we have our device. So we have put ion gel over those, as you can see here. So these are the two channels, and over those channels there is the our ion gel. So we will be starting to measure it. So let's put it on the semiconductor probe station. So it is very important to remember that we will be using 3 terminals. So one should be our uh, drain, and there should be our source and gate. So what I'll be considering is this terminal here. This terminal, this is coming from 1. So this 1 should be my gate part, and 2 should be my drain, and this 3 it should be my, as you can see, should be my source. So let's put the devices accordingly. I'm going to pull it out a little bit just to make sure we don't face any difficulty in measuring this. Okay, and for the gate, so your gate should touch the top of the dielectric ion gel, and your source and drain should be on the 2 sides of the semiconductor. So this is the connection. It's okay. So now let's go and I'm going to open up a program in K3 Semiconductor Characterization System. So let's open up. Let's go to my folder, and here you will find semiconductor. So what I'll do is I will start the kit and open up a project. This is my project. So let's go into that. Say no to all. As you can remember, our source was terminal 3, drain was terminal 2, and gate was terminal 1. So we'll be trying to put the system accordingly. Just wait a little bit so that the system is properly loaded. So you can use this gate software to measure diode, BJT, capacitor, GFET, MOSFET, etc. So I'm going to measure the characteristics curve BGS versus ID. So my as you can see, the gate is terminal 1, SMU 1, semiconductor measurement unit 1 means terminal 1, and 2 should be my drain, and 3 should be my source. So since it is a organic semiconductor, the carrier is majority carrier is whole, so I'll be using negative bias. So I'll be moving from 1 to -3 in a step of -0.02, and it will be a voltage sweep with dual sweep in linear scale, and then I will be using drain voltage to be negative -0.7, I think would be enough. So this is my initial condition for the drain and gate. So let's see what is the device characteristics look like. So here is the transfer characteristics in linear scale, and let me check. So go to access properties. Why? So no, it's the log scale, and for this one I think this should be in linear scale. So it's linear scale. So let's see the linear transfer characteristics here and logarithm transfer characteristics here. So let's go. Let's see. Hope the device will work. If our everything, our measurement and everything is okay, it should work. Yeah, the device is on. As you can see, it was on in around -2 gate voltage. However, there is a small hysteresis, as you can see. So small hysteresis means the device is synaptic properties is not that good. However, I'm going to save these things, save as, and let's see. Let's go and let's make a folder here. So today is January 23, 2024. I am using P3HT. Let's make it look good, and with PVDF-HFP. Both are wire with THF solvent. So I think this will be enough. So let's save it here, and same goes for this too. Let's select the folder that we have created. What is the folder here? Okay, same goes to here. Okay, so we have all this. Now what we'll do is graph 2 we'll just try to let's name it transistor 1. Let's use transistor 1. Populated it. Since there is 2 graph, I need to just name another one. Is like save all. So this is saved. Now what we can do is let's try to. This is our semiconductor. So let's try to do synaptic properties. So you need to come here, customs, under 4 terminal and FET and type Qs. So I'm coming here, and my gate is semiconductor measurement unit 1, as I said earlier. Drain is semiconductor measurement unit 2, and this is 3. So I'll be using around 3000 point for my pulses, and drain bias is 0.7. I use -0.7, but we can use positive for here just to to get the value more properly. I will be opening the Origin Pro here because I have some data saved here that will be using. These 3000 points, as you can see, these 3000 points are like values. So we'll be using steps. So steps mean 1, and the lowest for steps means 0 to 1, right? So for 1 we'll be using some value, and for 0 will not use value. So to give you a proper example of that, just let me just open my file. Okay, so here it is. As you can see, here is like 3000 points, and as you can see, like we can break down the whole step into 10 parts, and if the first part is 1, that means it's like 10% duty cycle, and if we use minus 2.25 for more than one cases, then we'll have more than 10% pulses. It will be 20, 30, etc. So what we need to consider here is this. When we are considering the BGS, as you can see, the turn on voltage is around here, so it's around between minus 2 to minus 2.7, somewhere in between. So we'll be trying to use this when the device is turning on. So minus 2.5 is a good approximation, I think, or minus 2.25 is also good. So we are using here, as you can see, the value is minus 2.25, so I think it's okay. So what we'll be doing here, we'll be trying to measure the long-term potential. So we need to give 100 pulses. So what I'll be giving is like, I'll give 100 pulses that will be ending in here. So it will end in around so 400 pulse, I need 1000 value, right? So for the first 1000 data, I need to give it some pulses. So yeah, so say for 1000 data, if I give 1 pulses for each 10 rows, and that means it will be like 100 pulses, right? So we'll be using this data value here, 3000, for the long-term potential calculation of what will happen after, and we'll see what will happen after, say we give 100 pulses and then give 0 values, so to see how much retention it could contain. So yeah, the 3000 values are done. We have given the gate bias also. Now let's see the output characteristics. So it will take some time. I will be running it and I'll come back after it's done. So we have measured the condition block, so let's have a check. So as you can see, what happens is like we are measuring the synaptic properties, so every time the condition is like in the lower side, we will consider only that part, so it's updating till this point, and then it's fundamentally reducing. So we just give you a little overview here. So as you can see, the synaptic properties of this device is not that much good, so it was not very good. I won't say it's a very good device for synaptic applications. So let's go and measure the second transistor.